In this session, we are honored to have Andrei Kolodny, a principal technologist in the CTO office at Wind River, to discuss ADAS in the modern vehicle.
As advanced driver assistance systems, ADAS, continue to evolve, modern vehicles are transitioning from isolated decision-making to a cooperative connected paradigm. This talk discusses the current state of ADAS and the next phase of autonomous driving, which is cooperative driving, enabled by collective perception messages and shared driving situation models. By leveraging cellular vehicle-to-everything (CV2X) communication, vehicles can share sensor data, detect hazards beyond their own line of sight, dramatically improving road safety and efficiency. Safety-critical ADAS use cases will be discussed as well, where one vehicle detects an approaching vehicle or pedestrian obstructed by another car and communicates this insight via vehicle-to-network communication, enabling surrounding vehicles to respond proactively. The talk will also emphasize the critical role of cloud-native architecture in the vehicle, CV2X and multi-access edge computing at the far edge to ensure low-latency processing and real-time decision support in these cooperative scenarios. Good morning, afternoon, evening, everyone. Today we explore the next evolution of advanced driver assistance systems, where ADAS, empowered by cellular V2X and edge computing, is shifting from isolated sensing to cooperative intelligence. By enabling vehicles to communicate and coordinate in real time, CV2X is unlocking new levels of safety, awareness, and responsiveness on the road. Together with low-latency edge processing, this evolution marks a major step towards truly connected and intelligent mobility. My name is Andrei Kolodny, and I'm a principal technologist in the office of the CTO. I'm responsible for leading technology strategy for next-generation software-defined vehicles, CV2X, cloud robotics, and edge-embedded systems. My main activities in this role include creating proof of concepts and prototypes to validate innovative technologies, as well as contributing to external-facing CTO activities, such as speaking engagements, writing white papers, and more. Before joining the office of the CTO, I served as a lead software architect where I have designed first Linux-based automotive infotainment system for BMW and developed first samples of autonomous driving systems. Let's explore how ADAS technology has evolved and how this evolution is deeply linked to changes in the vehicle EE architecture and connectivity infrastructure. In the early phases, ADAS was largely isolated effort. Each vehicle relied solely on its own sensors, radars, ultrasonic, and cameras. No data sharing, no external awareness. This setup has limited range, struggled with collisions, and had no situational context beyond the vehicle's immediate surrounding. As connectivity enters the picture, vehicles started exchanging basic messages, speed, direction, and location, using technologies like V2V or recently CV2X. This provided an extended awareness and helped in simple cooperative maneuvers like emergency braking alerts. However, it is still mostly reactive and data wasn't rich, just signals. The next leap comes with cooperative perception, where vehicles share sensor-derived insights like object detection and road hazards. This marks a shift from connected to collaborative intelligence. It enables coordinated decision-making, like jointly navigating an intersection or avoiding an occluded pedestrian, something impossible with isolated ADAS. This level of interaction demands low-latency communication, often delivered via 5G and MEC, and robust V2X infrastructure. Eventually, we move into full autonomy, where vehicles become nodes in a broader intelligent network capable of predictive behavior. The car is no longer a standalone system. It becomes part of distributed software-defined ecosystem, communicating with infrastructure, the cloud, and other vehicles in real time. This ADAS evolution goes hand in hand with a shift in vehicle architecture, from domain-based ECUs to zonal and central compute architectures, adoption of heterogeneous computing platforms, GPUs, NPUs, safety cores, introduction of containerized software, allowing faster updates and modular ADAS deployments, all baked by software-defined paradigm and cloud-native design principles. So, as we move towards higher levels of autonomy, we are not just adding sensors, we are reshaping the very architecture of the vehicle and its place in the mobility network. This slide presents Aptiv modular and service-oriented ADAS architecture designed for flexibility, scalability, and reusability across different OEM platforms. Let's start from the bottom, the hardware foundation. We have typical sensing and compute elements. IMU and GPS provide precise vehicle positioning and orientation. Cameras and radars handle environment sensing, covering both short and long-range detection. All of this fits into a zonal or central compute platform that runs the software stack. The software architecture is divided into clear functional domains and deployed in containers, allowing each component to be developed, validated, updated, and even licensed independently. Object detection and tracking. This layer includes both radar and vision-based perception, as well as AI/ML models for object classification and prediction. The Fusion module combines these sensor streams into coherent, high-confidence set of tracked objects. Environment model. Here we generate a dynamic representation of surrounding road. Occupancy grids, road models, HD map alignment, and localization all fit into real-time, continuously updated scene. Drive policy. This layer performs threat assessment, selects targets for planning, and computes optimal trajectories. It's where real-time decision-making happens, like merging, lane changes, or evasive maneuvers, all aligned with safety and comfort constraints. Actuation. Finally, motion control modules translate planned trajectories into precise vehicle movements, managing steering, braking, and acceleration. The key here is that each layer is architected as a containerized service which supports modular deployment, for instance, level 2+ versus level 4 functions, enables reuse across platforms and over-the-air updates, fits well into software-defined vehicle strategy, separating hardware from software lifecycle. This approach allows Aptiv to sell capabilities as modular, upgradable building blocks rather than monolithic systems. This slide illustrates how Aptiv ADAS platform offers a flexible modular architecture designed to scale across different vehicle models and OEM strategies. Let's break it down. First, hardware abstraction is key. The platform decouples software from hardware using standardized sensor and function interfaces. This means OEMs can customize their sensor suites and compute strategy without re-architecting the whole stack. Second, it features a common software platform. It enables reuse across product lines. By standardizing communication protocols and diagnostics, Aptiv reduces development and validation efforts, especially for safety-critical features. Third, it built for zonal architectures. In this model, sensors connect to zone controllers which aggregate data and forward it to central compute over a high-speed backbone. This results in a simpler wiring, better scalability, and clearer separation of concerns in the software stack. The platform comes in 4 configurations. Each is containerized over-the-air updatable and tailored to different levels of autonomy and feature complexity. Core, designed for entry-level ADAS, level 0 to level 2, hands-on, offers base safety and convenience features user radar, vision, and fusion. Plus adds hands-off level 2 plus capabilities with highway policies and automatic lane changes, starts integrating high-definition maps and radar machine learning. Pro extends support to all-road level 2 plus plus autonomy, machine learning assistant policies, and multimodal localization, ideal for more premium models. Ultra brings level 3 eyes-off feature for highway use cases, adds LiDAR, satellite cameras, and dual ECU for redundancy and higher compute needs. This modular approach supports OEMs in launching differentiated products quickly, reusing software across platforms, and prepare for software-defined zonal future. This slide highlights the integration of sensors, compute software, and DevOps to deliver scalable, safe, and intelligent driver assistance systems. We start at the top with the cloud layer, supporting automated simulation and testing that incorporates real-world driving variables, a concept known as a vehicle twin, a digital replica of the vehicle used to validate updates, test edge cases, and improve algorithms before deploying them. This allows for continuous learning, development, and validation even after the vehicle is on the road. Tightly coupled with the cloud is a DevOps pipeline, enabling rapid interactive development, safe and seamless over-the-air update, end-to-end traceability and testing. It is what allows the platform to stay fresh and improve over the time. Software applications. At the top of the in-vehicle stack, we have modular service-oriented ADAS features, supporting level 0, level 2 plus, like traffic assist or city pilot, highway level 0, level 3, including hands-free driving, advanced parking features, both automated and assisted. These applications are containerized for the flexibility and reuse. Below that, we have perception and localization, fusing data from radars and cameras enhanced with AIML to handle complex edge cases, a multimodal localization engine for robust positioning, a mapping system that aligns perception with HD maps and real-time updates. This enables the platform to interpret its environment accurately and in real time. Next in the middleware and OS foundation, powered by WinDriver, VxWorks, and Helix Hypervisor, ensuring safety and real-time determinism. It includes Aptiv's communication framework, core services, and edge intelligence, manages sensor abstraction, connectivity, and over-the-air update capabilities, and it forms a backbone of a platform reliability and modularity. Driving all this is the high-performance compute optimized for low-latency sensor processing and decision-making. It is built to handle the computational needs of vision, radar, AIML, and sensor fusion workloads. At the foundation are the sensors, a forward-looking camera, a driving monitoring system for hands-free driving compliance, up to 4 AIML-enabled radars supporting detailed environment sensors. This rich sensor suite forms the physical eyes and ears of the ADAS system. And it is not just a platform, it is a modular DevOps-enabled sensor-rich and AI-powered ADAS stack, proven in real-world deployment and designed to scale with OEM needs into the SDV future. Please follow the link at the bottom for more information. Let us look outside the vehicle. As we transition into software-defined world, the role of intelligent edge becomes increasingly critical. Data is no longer only processed in the cloud. Intelligence is being distributed across the entire ecosystem, from sensors to centralized compute and even to regional data centers. Let's break down this across the 3 main layers of the edge. First, the far edge. This is where data is generated. At the device edge, sensors like cameras, radars, and lidars in a vehicle start collecting raw data. Then, at the infrastructure edge, this data travels through the in-vehicle wiring to local compute units like ADAS domain controllers or infotainment systems, thus must act in real time to support functions like emergency braking or driver assistance. Next is the near edge or metro edge. This layer represents regional aggregation points like point of presence where data from multiple vehicles is transmitted via 4G or 5G. This metro nodes allows for real-time traffic analysis, fleet management, and rapid over-the-air updates closer to where vehicles actually operate. And finally, we reach the cloud, where deeper learning, long-term storage, fleet-wide analytics, digital twins, and model training take place. Data from vehicles is pushed through the metro edge into a centralized cloud platform over high-speed fiber. This is where strategic insights are developed, from improving software performance to enabling predictive maintenance and next-generation autonomy, testing various algorithms which we have discussed previously, and so on. And this pattern isn't unique to automotive. Every industry is moving towards the edge intelligence model. And this is really important to understand. For instance, in consumer tech, the far edge device is your smartphone cameras, while infrastructure edge might be the phone neural chip processing images locally. In telecom, radio unit is the far edge, and the base station acts as the infrastructure edge. In aerospace and defense, a radar of a jet is a device edge, and the plane mission system acting as a computer edge. And in automotive, the radar, camera sensors, and so on is a device edge. And vehicles, high-performance compute, car or truck form the infrastructure edge. This shift from cloud-only thinking to distributed intelligence is unlocking new opportunities for latency-sensitive applications, real-time decision-making, and the more resilient, scalable digital infrastructure. And the software-defined vehicle will evolve rapidly in this edge-enabled world. Here is an example of how to improve safety, comfort, and convenience through integration ADAS with a cloud-native software infrastructure at the edge. ADAS systems must react with some extremely tight latency budgets, about 200 milliseconds total, with minimum tolerance for error. The time is consumed across several critical processing stages. 50 milliseconds for sensor data processing, another 50 milliseconds for tracking and object fusion, 50 milliseconds for update the environmental model and generate driver assistant decisions, followed by motion planning, and finally, vehicle control and CAN transmission, all within a narrow 35 milliseconds window. This is where C-V2X integration and cooperative perception come into play. Let's walk through a real-world safety scenario where ADAS together with C-V2X can prevent collisions. We consider two use cases, without C-V2X support on the left and with C-V2X support on the right. Case 1 without C-V2X. Let's call it my vehicle. So my vehicle is waiting to turn left, but it is behind a large truck. There is an oncoming vehicle approaching the intersection, but it is occluded hidden in the sensor shadow, as you can see. So my vehicle can't see it, and its sensors can detect it either. But it starts turning left, a crash happens. So now consider case 2 with CV2X support. The same scenario, but now both vehicles are CV2X enabled and connected to the mobile network infrastructure via vehicle-to-network communication. Even so, the oncoming car is occluded. My vehicle receives its position and speed via CV2X by sending and receiving messages using 5G to the edge. Now it knows there is an approaching vehicle. It waits safely, let it pass, and avoid a crash. This is where 5G, ADAS, and CV2X shine, enabling cooperative perception and improving road safety in complex scenarios. So this emergency vehicle use case highlights how CV2X and edge compute enables cooperative perception in real time. Car 1 detects an approaching emergency vehicle, an ambulance. So ambulance is not sending any messages, but Car 1 sends out a decentralized environment notification message via CV2X, which includes direction of the emergency vehicle, whether lights and sirens are activated. This message is sent to the MAC, multi-access edge compute, which processes it in real time. The MAC forwards relevant information filtered by location and context to Car 2 via the 5G network. So Car 2 receives the alert before the ambulance is even visible. It can then take appropriate actions. For instance, lower the media volume, slow down, activate hazard lights, or change lanes. This showcases the power of cooperative driving enabled by CV2X, 5G, and edge computing, all working together to increase safety and situational awareness well beyond line of sight. Now let's take a look at the underlying architecture that enables the left turn scenario or emergency vehicle scenario we have just discussed. The key point, we don't need any specialized CV2X hardware for that. 5G network connectivity is sufficient to enable these use cases. Here how it works. Both vehicles are connected to MAC, multi-access edge compute via MQTT. They publish or subscribe to J2735 standard messages, for instance, BSM, basic safety message, or DEN, distributed environment notification message, via central MQTT broker hosted in the MAC. A CV2X application running in the MAC filtered these messages using geolocation and vehicle hidden direction. Based on that, it sends alerts to vehicles that are at risk of collision. Once a vehicle receives a warning, the ADAS system can take preventive actions. For instance, in the first case, slow down, cancel or delay a turn, or display an HMI warning to the driver. This is the first use case. Or it can change a lane, activate hazards lights. This is the second use case. This is how CV2X over 5G enables real-time safety without a need of extra hardware. In this slide, I want to highlight WindRiver's role in virtualization the edge network across industries, especially relevant in automotive and ADAS CV2X domains. So WindRiver's cloud-native container-based platform, which we have as a product, it is deployed by major mobile network operators across the globe. So it enables standardized interfaces, making integration easier for OEMs and Tier 1s a greater flexibility and scalability, faster delivery of new features and services, more cost-efficient and resilient architectures, connecting it to the ADAS and C-V2X use cases. So ADAS features need real-time, low-latency compute close to the vehicle. In cooperative perception, like emergency vehicle alerts or occluded intersections, edge nodes like MACs process and route safety-critical data. This architecture supports distributed workloads, so on the device edge, sensors and ECUs on the vehicle, edge data sensor at the multi-access edge computing, so real-time filtering and messaging like MQTT for C-V2X. The regional data center aggregates data, supports analytics and fleet-level intelligence, and the public cloud handles large-scale training orchestration over their updates. The diagram illustrates how compute location, latency, and workload source vary across layers. For ADAS and C-V2X, we target the edge data center layer, where we get less than 20 milliseconds latency, which is crucial for real-time safety decisions. WinRiver enables this device to edge to cloud continuum, making modern C-V2X and SDV architectures both possible and production ready. So we have discussed ADAS architecture and then briefly talk about in-vehicle or software architecture. But what would be the paradigm to implement in such a SDV architecture? There is a kind of uncertainty about how SDV software should look like. And what we propose, so here's an example of cloud-native vehicle architecture purposely built to support exactly these use cases. And there is a reason for that, to support the way how it should support ADAS and C-V2X workloads, alongside with mixed criticality applications. At the core, a safety hypervisor runs directly on the SoC to partition and isolate different OS instances, like a safety-certified real-time operating system, such as VxWorks for real-time ADAS tasks, or non-safety Linux or Android for infotainment or HMI. Each OS acts as a cloud node, complete with its own network agent, like a kubelet, to manage container workloads. By the way, VxWorks is the only operating system which provides a support for containers, which is important. And we have a VxWorks kubelet implemented as well, which allows our operating system being managed by the cloud-native paradigm software. So in the contents of ADAS and C-V2X, these containers may handle sensor fusion, perception models, and C-V2X messages, which we have discussed, this distributed environment message or basic safety messages, real-time policy evaluation. The central compute becomes the orchestrator, so effectively turning the vehicle into subcloud that can coordinate with the MAC nodes, which are also developed in this cloud-native paradigm, and by that it can just move workloads from the vehicle to the Mac and back and forth for cooperative driving features. This is critical here, and the orchestration of these mixed criticality workloads is critical. Safety critical workloads like trajectory planning, radar fusion, and non-safety, for instance, map updates, UI alerts. This might be handled differently, but remain tightly coordinated. This pattern extends into zonal ECUs and edge sensor nodes, as you can see on this slide. each also capable of running containers across real-time operating system or Linux. For instance, a zone controller may run ML inference locally while upstreaming metadata to the Mac. So some kind of distribute workloads between in-vehicle and outside the vehicle computation. And at the system level, Starling X runs at the edge, for instance, inside the Mac, handling orchestration and lifecycle management across vehicle and infrastructure. This is key for real-time V2X, where decisions might be offloaded or coordinated in under 20 milliseconds. What is the big advantage of that? So the uniform workload management across the vehicle and the edge. Whether a CV2X alert is processed in the vehicle or at the Mac, the logic doesn't change, just the execution location based on latency, bandwidth, or computer availability. So this is this is actually the big advantage: unified cloud-native architecture applied for the vehicle and at the edge. Let us talk a little bit about challenges. This is not a complete list, of course, it's much more bigger, but I think I have put most important ones. Maybe, I don't know, maybe we can discuss it during the Q&A session. And as we scale cloud native ADAS and CV2X, there are like both technical and strategic challenges. From a business model perspective, this shift introduces new dynamics. So OEMs might partner with or depend on telcos and cloud vendors. This is what now really happened with this 5G association and various PLCs. If you can go and look what kind of PLCs telcos are doing with OEMs, you can see this dynamic. So who owns the data? Who delivers the service? Who installs this MQTT broker or whatever broker at the edge, right? So which we have discussed. These questions are not fully answered yet. Then 5G Mac deployment at the far edge is not trivial. We have talked about, vehicle side, but there are definitely problems, or not problems, but challenges on the telco side as well, right? So while it enables real-time capabilities, it requires investment in infrastructure, local compute, and orchestration. It is an open question whether every region will support it uniformly and how fast it can scale globally. We know that even these V2X messages, they are different from region to region in Europe, US, and China. So security and data privacy are major considerations. Vehicles are sharing sensitive sensor data, location, behavioral data. This must be protected both in transit and at rest. And how we can trust this communication. For instance, you get a message alerting you, how you can trust that this is a not false message. Then the real-time performance is crucial. V2X alerts, especially for use cases like cooperative perception, requires less than 20 milliseconds end-to-end response. Reliable connectivity is a dependency here. 5G with Mac can help, but we still need a fallback strategy for a case where inconsistent network availability happens, right? So, and finally, interoperability is an ecosystem challenge, aligning across OEMs, tier 1 suppliers, telco operators, and infrastructure providers. This complexity is exactly why collaboration across industries is so essential. What are the important takeaways of this ADAS, CV2X, 5G, Mac interaction? As we look ahead, ADAS is transitioning from a system of isolated sensors to one of the collective intelligence. Through cooperative perception, vehicles can extend their situational awareness beyond the line of sight into areas occluded or hidden, dramatically enhancing safety. CV2X and Mac infrastructure are what make this possible in real time. They allow vehicles to coordinate, perceive, and react not just individually, but as a part of the broader connected environment. Cloud-native architectures are the backbone that enables this ecosystem to scale, flexibly deploying workloads where needed, whether in the vehicle, at the edge, or in the cloud. The big idea, the future of ADAS, isn't just about autonomy. It's about collaboration between vehicles, infrastructure, and systems working together to create safer and smarter roads. Thank you all for your attention, and I'm happy to take your questions right now.
Thank you very much, Andre. That was really interesting. As I said to the folks out in the audience earlier, this is the time to ask your questions because we don't always get access to somebody at Andre's level. So we do have a bunch of questions, so let's go through them. Let's see. Let's start with the rapid development of drone technology and flying taxis. Could you tell me the importance and also the need for ADAS in the road vehicles, especially cars?
I think it goes to the so each industry goes to the same direction, right? So these drones, it is not really automotive, but as we can see from our experience in aerospace and defense and the telecom, so everything goes to software defined, right? So and to have this unified architecture allows parties to put, containerized and virtualized, allows parties to put their workloads in some kind of unified environment, and then exchange the information. And of course, 5G, for instance, right? So it's a backbone where you can then exchange information between cars and drones and everything.
Okay. How are the security controls used during V2X? And are those also being considered for I'm not exactly understanding what this person is asking. Security controls for V2X. What's being considered? Does that work for you, Andre?
Yeah, so in the 5G, right? So in the 5G, you just when you deploy software which exchange messages, in my case, so what I have explained is MQTT, right? So and you go and deploy it on the cloud native platforms, and definitely in the cloud native platforms, there is a bunch of, or there are a bunch of security primitives behind, right? So you need to authenticate yourself, authorize, and there are various security protocols which are used.
Okay. Will there be bandwidth concerns with the number of vehicles on the road and the devices in terms of communication? That's a really good question.
Right, it's really good question. Well, yes, definitely there are concerns, right? So we have, for instance, it's not much about V2X messages, right? So because like they are not big, right? So in 5G, you can imagine that band is split. There is a dedicated slices, which and for if we talk about automotive, there are slices which provide the determinism and low latency, really dedicated to exchange, this machine-to-machine interaction, right? And it's not much concern about V2X messages, but we are considering, for instance, you can put video streams, right? So just not raw, but let's say pre-process, like send object data from ADAS to the edge to allow to process it there, and there might be I think it might be kind of concerns about the bandwidth. Yeah.
Okay. A similar question. There are many challenges in the 4G network. So how do we handle those network concerns?
Well, 5G is much more powerful than the 4G, right? So and becomes 6G as well. So the data throughput is much higher, and the real-time requirements are much better, right? So this is involving from the telecom side, if we are talking about really 4G and 5G.
Okay, let's see. What is the roadmap for Active to achieve its goals from sensing to cooperation in terms of a timeline?
Well, we are doing various POCs with the telecom providers about that, right? So Active has provided provides this ADAS stack, which is modular, right? So which is containerized and flexible, and based on the customer requirements can be adopted to the needs. And then as a next step, we are doing POCs at the moment with various telco providers of this V2X stuff to exchange messages. And so we are pretty much aligned with the whole industry on that.
Okay. Would you suggest a controller for ADAS if I wanted to do something, for example, predict pedestrians using cameras?
I'm not I'm not a hardware guy, but I would recommend just go to ADAS page of Active. There is a description what kind of controllers we are using there. So it's like I would say it's my let's say generic guess, it would be like a powerful CPU with some kind of GPU support and neural processing unit with some safety controllers which are on the same SoC, kind of this stuff. Just go on the to the Active ADAS page, please.
Okay. In the near future, some cars will be driven by humans, some by autopilot. How will they communicate with each other, and by what medium will that communication take place?
Well, we think that it will be 5G, right? Or 6G in the near future. So it will be really cellular network. Because look, I mean, this V2X story has started maybe 20 or 30 years ago, and not much happened there. And here with mobile network and cloud native approach, it opens really like a great possibilities to communicate like autonomous, non-autonomous cars with each other. Yeah.
Okay. Next one's a little longer, so bear with me. For vehicles with ADAS features, do we normally follow only ISO 26262, or do we also follow ISO 21448? And also, is that second specification applicable only to vehicles with a higher level of ADAS?
I'm not sure I know the second one, ISO 21448, you say, right? So
I am not familiar with that one either.
Either, right? So I would say, yeah. So normally, if we are talking about automotive, we are talking about 26262, right? So let me maybe put it off, take it offline, and then maybe we can tell more about that.
Sure. How do we assess the functional safety and cybersecurity goals for each phase from sensing to cooperation?
I think it's also a great question, right? So because definitely 5G provides a backbone which allows to communicate with low latency, real time, and determinism. However, if you're talking about vehicle itself, there is a well-established process how to meet all these safety goals. Well, if we go beyond the vehicle, right? So there are still open questions how you guarantee, for instance, safety if you start, receiving signals from the outside world. How you make sure that they are like false positive or false negative, not the false positive and not the false negative, right? So there are discussions around that still.
Okay. Another long one, but I like this one. Until now, cars haven't been dependent on other systems. Now we have dependency on a system that spans multiple technical and communicative layers, and it involves a wide variety of companies. How do we ensure that the system still works in 10, 15, 20, or 30 years? Some of these companies may not even exist by then.
Well, but it was always like that, right? So it was even worse maybe in the past because like OEMs got these black boxes with their ECUs with software inside, and they have no idea what is really inside, right? So they just provided a specification on some determinism and behavior functional, but what is inside was like a black box. Now is completely different. Now, like all OEMs just established their software teams, and they built. I will tell about that maybe a little bit. Yeah, like in my next talk. They built the whole stuff by themselves. Like look at the BMW. They for this Neue Klasse they use like 35K CPUs in the cloud to build everything. Now it's much more convenient and much more easier for OEMs.
Right. Okay. This is a Wind-specific question. How does Wind River's cloud-native approach help OEMs and Tier 1s manage the growing complexity of software-defined vehicles?
Well, I think Wind River is the only company which provides software for the devices and for the cloud, for the edge, right? So we do provide hypervisor and real-time operating system and also Linux on the device side. Beside that, we do provide container support and cloud management like Kubernetes support for the real time and for Linux. And also we provide our Wind River cloud platform for mobile network operators. This is also cloud-based, right? So and this creates, I would say, unified platform which allows our automotive customers and our mobile operator customers, our telco customers, to have a software which is unified and can speak at each other.
Okay, here's one that I probably would have asked. What's better, discrete ADAS or integrated ADAS with a domain controller?
I think the whole industry just goes to this, to this up approach, right? So where you combine your software into one box, right? So it gives particular advantages in terms of let's say flexibility and resources usage and unified platform. all of this stuff. So means if it is a separate, if it will be like a domain controller box, right? So there are definitely some constraints on that, right? So in terms of like, let's say, okay, you need to apply for this controller particular compute budget and cabling and all this stuff, right? So which is definitely a little bit disadvantageous. That's why the whole industry goes to the central brain.
Okay. Winding down here, what role do telco and infrastructure edge partners play in enabling real-time decision-making for next generation ADAS systems?
Well, I think that there is a strong push from telco to use to work with automotive now. And I think the reason for that, then now they deploy this 5G infrastructure, right? So and with 5G infrastructure, they have this multi-access edge compute where they have computing power, right? So and it is a great possibility for telcos now to come back and to talk to automotive, how to work together to use it and to have various use cases around autonomous driving.
Super interesting, and we had a ton of questions, which is great. So thank you again to Andre. Thank you to Wind River for sponsoring this event, and thank you to the folks in the audience for your participation. Bye-bye, everybody.